All right, and welcome back everyone to what will be, I believe we can do this in one video. This will be our final video for the semester. And there was much rejoicing in the kingdom. Yes, I can hear you through the interwebs. Yes. So, what we're going to finish up with this semester is a prominent application of the singular value decomposition. And what this is going to entail is more or less a short review of statistics and also kind of a quick outline of how we can use the SVD to come up with this sort of trend recognition, or what are called principal components. And we are going to kind of give this some context. So bear with me as we go through a brief review of statistics and kind of give it some linear algebra context. And then we'll go ahead and try to finish up in a reasonable amount of time with a quick application of the singular value decomposition. So let's begin as we would with just about any sort of statistical analysis. We are given some sample set of data, right? We have some study wherein we collect numbers, right? And this is just going to be some subset of the reals, right? So they're going to be real data entries. So this is going to be a continuous random variable that we're sampling off of. And we're going to compute the mean of this data set, and this is nothing more than just the expected value, right? This is our sum of all the data and dividing it over how much data we have. But we would also like to not only know what that mean is, but we'd also like to make sure that that mean is kind of standardized. So much like we do with a bell curve, so our normal distributions, we tend to shift them over to the origin. So what we're doing here with this normalization, the idea of normalization is to shift all of your data over to a location relative to the mean of that set. So what we create is a vector A that is going to be composed of a whole bunch of differences, and it's just measuring how far away and in which direction each data point is from the mean of the data set. No problem there. And we can check indeed that the norm, or sorry, not the norm, the mean of this data set is 0, right? So that, right, the mean of the data, once it's been normalized, is actually 0, as we need it to be. So if we have some arbitrary vector x coming from Rn, then we can write A simply as this difference of two vectors. And this is just a way for us to do all of these computations for normalizing the data at the same time. So instead of doing one by one, we just, instead of normalizing each data component one by one, we do them all in one fell swoop. And we make use of this vector E, which is going to be the vector of all ones. Right, this is a useful tool for us, especially if we have repetitive operations that we need to employ over an entire vector of data points. And more to the point, not only do we get the normalized data out of this vector difference, we can also figure out what the norm looks like, or not the norm, the mean of the data, by taking the dot product of x against this E vector and dividing by n. So in some sense, we actually get a brand new inner product on Rn by taking this guy to be our notion of the inner product. So we actually change the dot product a little bit, much like we did for discrete Fourier transforms. But I digress. So this means that this A vector can actually be written as this matrix difference, I minus 1 over n times E, times this vector x. So there is a linear operation or linear transformation that takes your data to its normalized data set. And this capital E matrix is just going to be the outer product, or rather the projection matrix associated with the vector little e. This is a rank 1 matrix, and it actually is just the matrix containing only ones. So we can continue. So not only do we want to compare the mean of our data, we want to figure out what that is. We'd also like to figure out what the variance of the data is, and that's our standard definition here, that we have this sum of squares, right? We are effectively just taking the 2 norm of our data against the mean and scaling it by some normalization factor or prefactor, some people call it. So we're just figuring out how far away our vector is from the mean vector, from the constant mean vector. So we usually take, so for a standard procedure, we usually just take this new constant to be 1 over n minus 1. And you'll see that in your standard, that would be, well, what would it be? It's a standard z-score or standard hypothesis testing. You're going to see it used in that way, or used in that setting. Then we can go ahead and define not just the variance, but we define the standard deviation of our data set as being the square root of the variance, the positive square root of the variance. So all we're doing in this quick review is showing or giving you an idea of what the what statistics looks like from a linear algebra perspective, or that we can go ahead and use linear algebra to study statistics. So suppose that we had not 1 but 2 data sets, right? The same size as before. So we effectively think of this as running 2 experiments and collecting the same number of samples off of each experiment. Then what we'd like to do is to construct the same quantities of mean, variance, standard deviations of the second set, but we are going to compare that second data set against the first. So this is a correlation data set. We're trying to figure out how these two data sets vary with respect to one another. And these guys can vary in a lot of different ways, but in particular there are a few that make more sense than others. One, we're effectively trying to figure out how much these guys are moving with or against each other with respect to a linear regression. So if I'm looking at each one of these data sets, I'm looking at these and saying, okay, the first one looks like it's got a positive slope to it, so these guys are basically in perfect alignment with one another. They vary at the same in the same way, so they are covariant. You also have in number 2, they could be contravariant. They could be related to each other in opposite capacities. And then, of course, there is the I have no idea what this data set is doing option, where this correlation constant would actually be totally insignificant to us. It would be irrelevant. We wouldn't be able to get anything off of this data apart from saying, well, it's definitely probably not a line, or it doesn't live on or near a line. So what we're going to do here to measure this correlation between the 2 data sets is define something called the covariance. So not the variance, but the covariance of the 2 data sets. And this is quite literally just going to be the dot product, a scaled version of the dot product between these between the 2 normalized data sets. So this again shows the ubiquity of linear algebra showing up here. This usually awful definition that we have to deal with from just putting stuff into a computer directly is actually very easy to employ from a linear algebra standpoint. So what we're going to do now is notice that if we are comparing against the same data set, then we actually get the usual notion of variance. So what we're going to do is define this rho sub xy that I had labeled up here in the previous example, but didn't give it any context apart from saying it was a correlation, a measure of correlation. Well, here it is. Here's the definition of what a correlation constant looks like. Now, what we're saying is that if rho sub xy is a positive number, then the data is positively correlated. They are correlated. If rho sub xy is a negative number, then this guy is these 2 data sets are going to be anti-correlated. They vary in opposite directions. And the closer we are to 0 just means the less correlated the data is, and there's not a whole lot of statistical evidence to show that the data are correlated with one another. But we can notice that due to the Cauchy-Schwarz inequality here, that our correlation coefficient actually is stuck between plus or minus 1 when we drop the correlation when we drop the prefactor. So the point is that this correlation is stuck between, or this correlation constant is stuck between plus or minus 1 for all intents and purposes. And it gives us a measure of whether or not the data are varying with or against each other. So what we're going to do now is ask what happens if we're given a sample set with distinct measurements on n quantities. What happens if we go ahead and throw these guys into the same matrix, or the same? We're going to compare these guys against each other. So we're effectively running the previous analysis for not just an x vector and a y vector. We're running this for an x1, an x2, x3. We're effectively running the same experiment over and over and over. And we're going to wind up constructing a matrix, or we're going to construct a data matrix where the columns of that data matrix are the individual experiments. And we get our data from each of these experiments, and we just lump them together into one matrix. Right, and this comes up in both of the image compression and handwriting recognition projects that I put out for you for your final project. So this is going to be the setting that you're going to have to deal with. So what you're going to do is define a mean vector, much in the same way that we did for the previous setting. So we're going to go ahead and write this in matrix vector notation, and notice that this is a multiplication by the column vector E of all ones, right? So this is a column vector multiplying into an n by n matrix. So let me see if that actually does that make sense. Yes, it will. So I think I actually need to transpose that guy. Yeah, I'm pretty sure I do. Okay, right, otherwise the dimensions don't match up. There we go. Much better. So what we're going to wind up doing here is normalizing the entire matrix now with respect to each experiment. So each vector, each column is going to get its own mean, and we're going to normalize the data in each column by that mean. We're going to center everything around the origin in Rn. So that creates this normalized data matrix A. And we construct that guy just like we did on the previous page, but instead of just multiplying by a single vector, we multiply by all the vectors. Multiply by all the vectors, yes. So what we wind up with now is a question of how do we compute the variance or the covariance or the mean or the standard deviation of these all these experiments related against each other. And this drives us to the following matrix. We're using K again because that is our standard notation for a positive definite matrix. And we can see that it is a positive definite matrix in the following way. A transpose A, if I ask what that is exactly, notice I get this sum. And this, statisticians will recognize as the definition of covariance, right? So these sums are going to be taken over. Well, it's just going to be this matrix multiplication of A transpose with A, and it effectively gives us all the covariances between each pair of experiments. So sigma sub xi with xj tells us the correlation between each of these guys, the covariance, between each of these experiments. So in particular, to find the variance of each one of the sample vectors, you're going to look along the diagonal of this matrix K. And K, as you might guess, is called a covariance matrix. Now, it is defined as a Gram matrix. This is A transpose times A, so we're going to get a whole bunch of Euclidean dot products in here. But Gram matrices can be either positive definite or positive semi-definite. In a statistical setting, it is almost never the case that you get a semi-definite matrix, or that you don't get a positive definite matrix. Being semi-definite would require that you satisfy this condition on linear dependence condition, and that's guaranteed to almost never happen, right? The probability that you wind up with one of your experiments as being a combination of the others is like there is measure zero. There is probability 0 chance of that happening. So it is safe to assume in a general or a generic setting that your Gram matrix or this covariance matrix is actually positive definite. So we know lots of interesting properties about positive definite matrices that we can start to use. And as a general remark here, we don't have to make sure that X is a square matrix. We can go ahead and take this on a general m by n set of data. So each individual, there will be n experiments, but only m measurements taken for each experiment. And this is going to be the case for each of the final projects. So both of these are going to have to use this general rectangular setting and create covariance matrices. And the reason why we want to do this is the following. So consider the application that is becoming more and more ubiquitous in our in industry, in technology, where we wind up getting and retrieving for ourselves a massive quantity of data, and we need to be able to parse through it and figure out what the general trends of these data are. So one particular example, you can think of search engines. There are millions and millions of visitors to web pages, and frankly, that's probably even an underestimate. It's probably on the order of billions. There are billions of visits to websites in a given day. So we're already looking at a gigantic data matrix that we have to parse through. And this is impossible for us to do with our puny human minds. We do not have the capacity to organize that much information and make any sense of what's happening. So what we try to do here is follow the math, or figure out a way to compress that data into something that is a little easier to handle. So what we typically look for are the trends in the data set. So we can try regression analysis to carry this out, but that requires modeling the data set, and we have no idea what that data set looks like because we can't picture it. We can't figure out what this gigantic billions by billions matrix looks like. So it's much better to figure out find those vectors that capture the most variance in the data. Right, this is where the greatest deviation from trend is going to be, and they're effectively behaving like our eigenvectors from before. They're telling us where this data matrix wants to throw the most information about the matrix. Along which directions do we want to throw the most information about the matrix? And the goal then would be to find the trends specifically in the covariance matrix of our data. So if we look at all the vectors in a set E, which is actually probably a terrible notation. Yeah, let's go ahead and change it. Probably a terrible notation because we already used E from before. Let's go ahead and call this guy, I don't know, J for Jerry. I don't know. There we go. So if we look at all the vectors in the set, effectively the image, the image of A along the unit sphere in Rm, then we can try to maximize the function, the quadratic function here, where Q just literally spits out what the standard deviation of that experiment is, of that particular unit experiment is. And if we follow this carefully, we'll actually see that this is a quadratic form, right? Hence the Q. Right? We're figuring out how to maximize this quadratic function or this quadratic form over all unit vectors in Rm. So this is a constrained optimization problem now, which we actually solved a version of back in chapter 5. And in fact, we can use new technology, new tools here to solve that problem. Right? In particular, if we construct the singular value decomposition of our covariance matrix K, then this maximum is exactly what is produced. right? We already figured out that the largest singular value is the 2 norm, right? So the 2 norm of k and the dominant singular value of k are exactly the same. So in particular, the dominant singular vector gives us the direction of greatest variance in the data. So each subsequent vector accounts for a little bit of extra variance, and these guys are all going to be perpendicular to one another because we designed our singular vectors to be an orthonormal set. So we're effectively picking out all of the different, all the greatest directions of variance that we see in our data. And the singular values are going to be getting smaller and smaller and smaller, so we're going to be contributing less and less and less trends to the data the further we go, the further down the list we go. So we're effectively tracking how much of the data is accounted for when we look at the principal or at the singular vectors. We're figuring out the singular values are telling us how much of this covariance data we see and in which directions. So moral of the story here is that if we compute the singular value decomposition of the covariance matrix of our data, then the jth singular vector qj accounts for exactly this much of the variance in the data set. And the rank k approximation accounts for mu, right? So mu here is technically going to be mu sub k. And this is telling us what proportion of the total amount of variance we get in the data set. And for your projects, this quantity here is going to be very important. It's going to tell you how much of your data is pointing in which direction. So if you're asking for 50% of the data, 75%, 90% of the data, right, there's going to be a k that you have to compute here. You have to figure out how many singular vectors are going to get you that much data. But we do have a nice characterization of how much of the data is in there by computing this ratio of how much variance is contained in the first k singular vectors divided by how much total variance there is in the set. So as a remark, the projects ask for this standard deviation progress instead of variance progress. So technically, to be a little bit more precise, you should be using the latter, but you are welcome to use either the standard deviation, so you don't have to use the squares here if you find that your analysis is more complete without it, or a little more informative without it. But yeah, you're welcome to go ahead and use the standard deviation as a measure of how much variance you're accounting for in your compressions or your or recognitions. So the convention would be that the vectors that belong to the Q matrix in the singular value decomposition are called the principal vectors, while the vectors of P are called the principal coordinates, right? And you can see that in how these guys are strung together in terms of weights and in terms of which matrix is going to give us, or the linear combinations of which vectors we should be using to reconstruct our data. So all in all here, this process of organizing your data into a matrix, normalizing that matrix against a whole bunch of different means, constructing the covariance matrix, and then factoring it into a singular value decomposition, and then using the singular vectors of that decomposition to account for a certain amount of the data, a certain amount of variance of the data. This whole process is called principal component analysis. And many occupations where you're dealing with statistical analysis or risk assessment, or just about any job where you have to analyze large collections of data, you're going to have to know how this process works and what it's really doing for your data and what it spits out when you're all done. So many jobs will ask you to perform this kind of analysis. So what you should be doing here is focusing on how that process acquires trends. So we're effectively just taking general eigenvectors, or a generalization of eigenvectors, to account for trends in covariance. And that's going to give us the primary trends, or the primary vectors, or principal vectors, that tell us exactly where most of the data is focused. And you can usually take these gigantic matrices of millions by millions of entries and reduce them down to something like maybe on the order of 50 or 60 vectors instead. You can capture something like 85 to 90% of the most data sets in just the first 100 or so principal vectors. And that to me is absolutely remarkable, that you can take this data set of millions upon millions or billions of vectors in your data matrix and reduce it down to the point where you get virtually all the information in your set or in your experiments by just using the first 100 or so principal vectors. And that is a staggering reduction of information. But what you lose in not accounting for that tail end of the trends is totally outweighed by how dramatic the reduction in size of your data matrix is. So usually we're willing to take a certain cut in resolution just so we can get a general idea of what trends look like. So that is it, actually. So that is the end of this video, the end of principal component analysis, the end of eigenvectors and eigenvalues for practical linear algebra, and the end of this class as a whole. So thank you all for coming along for the ride. I've had a lot of fun putting together these videos, and it's always a joy to teach this class. There's a lot of opportunity for showing the practicality of math. So those questions of when am I ever going to use this? Well, this is one of the classes that answers it just to its face. So I hope you find this information useful, that you look for applications of linear algebra wherever you go from here. I guarantee you that you will see linear algebra somewhere now moving forward. And honestly, I think this is probably one of the more powerful tools in your toolkit. That and calculus, but I digress. Thank you for coming along for the ride with me. And, well, there is no